Step into any major industrial manufacturing facility today, and you are constantly surrounded by immense, powerful rotational energy. This image shows a massive turbine rotor being lowered into place. The primary engineering hazard here comes from the intense inertia forces generated by the sheer mass of these moving components. In a theoretical model, a rotor's center of mass aligns exactly with the physical axis of the shaft. However, manufacturing is never perfect. When a rotor's center of mass deviates even slightly from its true physical axis, it creates a condition known as eccentricity. This stress analysis illustrates what happens when an eccentric mass spins up to high speeds. The microscopic offset generates violent, unbalanced centrifugal forces that warp the machinery. These outward forces rapidly increase the loads on the internal bearings. Over time, this repetitive stress threatens the structural integrity of the entire chassis and produces dangerous, escalating vibrations. Simply adding thicker steel to the casing cannot solve the problem. To keep the machine from tearing itself apart, engineers must actively calculate and zero out the unbalanced forces. Any mass moving in a circular path requires centripetal acceleration. This produces an equal outward centrifugal force. As RPM remains steady, the force magnitude stays constant, but its direction constantly rotates with the shaft, creating a moving point of stress. The core objective of dynamic balancing is to design and carefully place secondary countermasses onto the rotor that perfectly cancel out those rotating dynamic loads. We will explore how engineers use vector mathematics to achieve exact equilibrium in purely rotating systems, and why that exact same math fails completely when applied to reciprocating engines. Balancing a machine is an exercise in neutralizing hostile geometry. We begin with a system suffering from a single offset mass, indicated here in red. As the shaft spins, it generates a single outward centrifugal vector. The simplest solution is to attach a secondary mass of equal weight, exactly 180 degrees opposite the first. Because the masses are equal and directly opposed, their centrifugal force vectors are now perfectly equal and opposite. They cancel each other out right at the center axis, leaving the shaft completely neutral. But industrial rotors rarely have just one point of unbalance. They typically have multiple masses of varying weights scattered randomly across a single plane of rotation. Tracking and solving the intersecting angles of a multi-mass system using only analytical algebra is tedious and introduces a high probability of human error. Engineers require a faster, highly visual tool to synthesize all of those competing directional forces into one definitive solution. That tool is the polygon method. It is a graphical technique used to calculate the exact countermass needed for any complex rotor. Step 1 is to calculate the raw centrifugal force for each individual mass based on its specific weight and radial distance from the center. Step 2 requires converting those disparate force values into a consistent linear scale that can be drawn on paper. This gives us proportional vector arrows representing the magnitude of each force. Crucially, the exact angular relationship between these forces must be strictly maintained relative to a horizontal reference axis. Moving to step 3, we take our scaled vectors and draw them tip to tail in sequential order, maintaining their precise angles. Notice the gap between the start of the first vector and the tip of the final vector. This gap represents the sum total of the system's instability. For step 4, we draw a new line, the end segment, connecting the start and end points, physically closing the polygon. Measuring the length of this end segment and its angle relative to our grid reveals the exact magnitude and direction of the rotor's total unbalance. Step 5 finalizes the process. The exact opposite of this end segment dictates the weight and angle of the final balance mass required to neutralize the entire system. We have successfully stripped away the physical hardware and translated abstract physical forces into purely geometric lines. This visual shows a multi-blade turbine rotor where these principles are applied. The mathematically derived balance weight is physically attached directly to the hardware to stabilize the spinning assembly. By closing the polygon, engineers achieve complete dynamic balancing, ensuring stability in pure rotational systems. But there is a mechanical architecture that defies this complete balancing, the steam locomotive. Instead of pure rotation, a locomotive generates power through the intense, repetitive back-and-forth motion of a heavy steel piston, firing inside a large cylinder. A reciprocating mass generates a linear disturbing force. If we attach a rotating counterweight to perfectly cancel that horizontal force, we create a new problem. As the wheel rotates, this counterweight generates a massive, uncompensated vertical force perpendicular to the stroke. In reciprocating engines, completely neutralizing a force is a geometric impossibility. You can only relocate it. Look closely at this image of locomotive driving wheels. You can see how engineers physically implement these flawed rotating counterweights, cast directly into the red sections of the steel. The first destructive symptom of that relocated vertical force is known as hammer blow. When the counterweight rotates downward, it pushes the wheel so hard into the steel rail it can damage the track. When it rotates upward, the wheel lifts, losing traction before slamming back down. The train also suffers from variation of tractive force, meaning pulling power oscillates, and a swaying couple, forcing the chassis side to side. To manage this, engineers rely on a compromise known as partial balancing. We accept a certain amount of horizontal swaying to prevent the wheels from producing catastrophic hammer blows that would destroy the tracks. In complex linkage assemblies like this one, the standard engineering practice is to fully balance all the pure rotating masses, but only apply enough counterweight to balance a fraction, typically 2/3, of the reciprocating masses. While pure rotation allows for mathematical perfection, advanced engineering often demands calculating the safest possible distribution of unavoidable physical flaws.